This is a solid cylinder rolling down an incline. Now the height is h, but the total height is also, we need to also include this r for total height from the ground. The length of incline is, let's use L. We are going to solve for acceleration. A is the question. There are three forces on the cylinder. Gravitational force, mg. Another is normal force. Okay. And then friction force. And this is static friction force. The cylinder is rolling down the incline without slipping. Therefore, friction force is also not doing work on the object. So when we write work energy theorem, the total work done on the system is 0. So therefore, we can easily switch to energy conservation method. So we write the energies at the beginning and energies at the end of the incline. At the beginning, we have potential energy mg h plus r, and because object is stationary, there is no kinetic energy at the beginning. At the end, kinetic energy 1 over 2 mv square, and rotational kinetic energy 1 over 2 I omega square. Omega is the angular speed. And also we still have some height here from the ground as it comes down to this at the bottom of incline. So this height has to be considered as r. Therefore we still have some potential energy mg r. To simplify, I'm going to rewrite as mgh plus mgr equals 1 over 2 mv square plus 1 over 2. Instead of I, this is moment of inertia. Moment of inertia of solid cylinder is given as 1 over 2 mr square. Okay. Instead of omega, let's recall linear speed is v, angular speed is omega, and omega r. Omega r is linear speed. From here, omega is v over r. V over r, but it has to be square term. And plus mgr. Drop m's from everywhere. We have r square term, and r square comes from there. We can also drop that. So what is left? gh plus gr equals 1 over 2 v square plus 1 over 4 v square plus gr. So we have the same term on both sides. We can also drop this. But when we rewrite, it is nothing more than gh 3 over 4 v square. V square turns out to be 4 over 3 times gh. Recall time-independent kinematics equation. V square equals v naught square plus 2 times acceleration times delta x. Initial speed is 0, so we drop this. Instead of v square, we can write what we found. So that is 4 over 3 gh, and 2 times acceleration times delta x is the length that the block slides from this point to all the way down to this point. So that is L. Solving for acceleration, we have 2 over 3 g h over L. H over L is h is the opposite of this angle theta, and h over L is the sine. So instead of h over L, we can also write sine. So acceleration is 2 over 3 g sine theta. So we used energy conservation method and found acceleration. And next we are going to use another method, which is torque method, and also Newton's second law to find acceleration. So tau net torque, moment of inertia I, times the angular acceleration of the object is alpha. When we look at this cylinder, there were 3 forces. So force 1 is friction force, static, in this case we'll use maximum. So it has a lever arm distance r. So we can write that Fs max times r. And when we look at other forces, so notice mg is now passing through the rotational axis, so the torque is 0. And again, normal force is passing through the rotational axis, so based on this also 0. So this is the net torque, Fs maximum times r. Moment of inertia I, recall we wrote 1 over 2 m r square. Moment of inertia 1 over 2 mr square, and alpha is angular acceleration. The relation between linear acceleration and angular acceleration is alpha r. A linear acceleration equals alpha angular acceleration times the r. From here alpha is a over r. Doing some simplification, Fs maximum equals 1 over 2 ma. Fs maximum is given in terms of static friction coefficient mu s and normal force. Don't recall that force mg downward, when we decompose this into 2 components. One is parallel to the motion, this mg sine theta, and the perpendicular component of mg is mg cosine theta. This mg cosine theta is basically the normal force. Okay. Now we have also friction force backward, F in general. So this friction force, if object is sliding down with a constant speed is not changing, and the friction force, kinetic friction force, is as big as mg sine theta. Going back here, we need to write normal force. Normal force is mg cosine theta. So we just write mg cosine theta here. That is 1 over 2 ma. After some simplification, a is 2 mu s g cosine theta. Now we need to write Newton's second law. Newton's second law tells that net force is m times the acceleration of the system. Net force. Now object is moving forward down the incline. That means mg sine theta is positive direction, pulling it mg sine theta. And friction force, static friction force, is mu s. We just wrote here. I'm just copying this here. Mu s mg cosine theta. Mu s is a over 2 g cosine theta. So mg sine theta minus a over 2g cosine theta. That's for mu s. And then copy the rest, mg cosine theta, mg cosine theta equals m times acceleration. After some simplification, it's like cosine to cosine, g, but m is showing up everywhere, m, and m. So eventually, after the simplification, we have now g sine theta minus a over 2 equals a. A equals 3A over 2 equals G sine theta, and A turns out to be 2 over 3 G sine theta.